By the way, as you may have noticed, this is a children's museum, so there's little kids flying around this normal. Be nice to them. Also, how are you feeling about the microphone in the back?
Yeah, if he's not here, is this audible if I speak?
Yeah.
It's like this in the back.
I think Mike will be better.
I'm getting
There's lots of seats.
hello.
If it's too loud, it's loud. So hello everyone. Hope the class is good. Okay. So thanks to the organizer for organizing this, and thanks everyone for attending my talk. Today I'll tell you the story of the Gao-Wald theorem in dS-JT with timelike boundaries. So this is based on some work I uploaded earlier this year. It was sort of a small project that came out of this more detailed work with these collaborators, Bruno, Eva, Gonzalo, and Sanjay, where we studied how to consistently add matter to the PT bar plus lambda duality for the sitter space that describes the sitter space with a timelike boundary. So in particular, this theory consists of multiple states, and the state with an excited with the cosmic horizon, the sitter, is described as an excited state in the dual theory. And also this work takes some inspiration from this earlier work by Adam Levine and Edgar Shadurian, who studied a similar question, but in dS-JT gravity without timelike boundaries. So in addition, I would like to thank Eva and Edgar for many good ideas and useful discussions, and also my JF referee for many interesting questions that made me think deeply. Okay, so I'll just start by introducing what exactly the Gao-Wald theorem is. So stated most simply, the Gao-Wald theorem states that matter that satisfies the null energy condition makes the sitter taller. And what this means is that an observer that lives on one pole of the sitter space, for instance this left pole, can eventually receive a signal from the other pole and so view the entire space. So over here, this observer cannot receive any signal from the other pole. However, after this time, an observer on the left can receive a signal from the other pole of the sitter space. So recent years have seen a lot of progress in the sitter holography, where the dual theory is defined on some kind of time-like surface in the sitter. So it could be some kind of time-like boundary, where I've pictured the state where we fill in the sitter space with a horizon. Or this theory could live on some observable line, or some kind of stretched horizon. So the common feature between all of these theories is that the holographic theory is in some kind of time-like space. And the Gao-Wald theorem suggests that the theories describing these two static patches need to be coupled in some way. So in particular, it should be possible to send a signal from one side of the sitter to the other, in some excited state of the matter, but not in its ground state. So that's kind of interesting and paradoxical, and we would like to study this more. However, the ground state of the matter is not truly empty. There is a non-zero Casimir energy that arises because you impose some boundary conditions on the matter at these time-like surfaces, like the boundaries of the observers. And this Casimir energy has some back reaction that changes the causal structure of the space-time. And in addition, the assumptions of the Gao-Wald theorem are also violated when we put in time-like boundaries in the space.
Sorry, I'm still confused about a silly thing. The two things that are already communicating, I mean, that are supposed to be not communicating in the ground state. In most of your pictures, they work like not at particle zero or the north and south pole. So then they would be able to communicate in the ground state, right?
So here they are still causally disconnected. So if you see this picture, if I send a null geodesic from over here, for instance.
Oh, and they stay outside of the right?
Right, so they still are causally disconnected even though they are
Thank
connected.
you. Yeah.
Okay, thanks for the question. So So when we put in these time-like boundaries in the space-time, that also violates the assumptions of the Gao-Wald theorem. So we don't have some compact spatial slice or null geodesic completeness. So the question is, how does this alter the conclusions of the Gao-Wald theorem? Does it make de Sitter space fatter instead because we have some kind of negative Casimir energy? So in this talk, I will test this expectation in a simple 2D setup with the matter content is some conformity theory. And in particular, we will find that in this setup, it's possible for the space-time to become weakly taller or weakly fatter instead. Where I will define what I mean by these terms, but it's sort of different from the naive expectation. Okay, so here's just an outline at the start of how we might attack this question. So first I'll just introduce the setup, which is time-like boundaries in de Sitter-JT gravity. And then I will explain what exactly I mean by the space-time getting taller or fatter. And then we'll move on to the fun part, which is actually computing this Casimir energy and finding its back reaction on the space-time and seeing if it gets taller or fatter. And then I will end with some future directions. Okay. So the set of the relevant parts is JT gravity, and the relevant parts of the action are the ones that I've shown here. So in particular, there is a field phi, which is the dilaton field. And there is also a Gibbons-Hawking-York boundary here, which is there because we have time-like boundaries, and it's there to have a well-defined variation of principle. In addition, we have some matter CFT. So if we do the integral over phi, that fixes us to r equals 2. And in particular, we will work with the solution where the metric is given by the following expression. So sigma is some time direction and phi is a spatial direction. And also if we find the vacuum solution for the dilaton, we find the following expression given here. Here phi sub r is some unfixed constant, whose meaning I will explain more in later slides. So in this setup, we place time-like boundaries at the following locations where the dilaton is constant. So just to be clear, here beyond the locations of the time-like boundaries, we cut out the space-time that is in here.
Is there a reason why it's preferred to get constant dilaton?
Yeah, so that's exactly what I'll explain here. So before I explain that, note that the locations of these boundaries are parameterized by this parameter zeta, and if I increase zeta, these boundaries become closer. So now why do we place these boundaries at constant dilaton? And the reason is that we want to mimic the setup of interest in higher dimensions, which was studied in these papers, where we studied the PT bar plus lambda 2 duality in 3D with matter and 4 dimensions by Ivan Gonzalo. And in these setups, the boundary is some cylindrical boundary that has some fixed proper size. So in this setup, the dilaton is related to the area of the higher dimensional transverse sphere. In the picture where you get de Sitter-JT gravity via some dimensional reduction. So fixed area of the transverse sphere is like fixed proper size in the circle. And one thing that's useful to note for this talk is that the value of the dilaton at the horizon is a measure of the horizon entropy. So there are multiple pictures where we might get de Sitter-JT gravity via some dimensional reduction. And in both pictures, the dilaton is related to the horizon entropy. So in particular, in the vacuum, where we don't have any matter content, this parameter phi sub r is related to the horizon entropy. In this talk, we will focus on the case where the central charge of the matter is much smaller in units of this parameter phi sub r, so we can compute some kind of correction to the vacuum, and some kind of correction due to the presence of this matter. Okay, so back to the setup. So in this problem, we want to compute some kind of back reaction of this Casimir energy. And when doing that, we fix the value of the dilaton on the boundaries. So we are fixing the proper size of the cylinder. So that's related to fixing the value of the dilaton on the boundaries. And we fix it to the following value. So the next question to ask when finding the back reaction is, what are the dynamical degrees of freedom that change in response to some matter source, some non-zero stress tensor? And this is the dilaton, whose equations of motion we can find from the action, and it's sensitive to some non-zero stress tensor on the right-hand side here. And also, another degree of freedom is the extrinsic curvature of these boundaries. Now, this might be a bit unintuitive, but since the metric does not change in this setup when we find the back reaction, the second degree of freedom is equivalent to the coordinate locations of the boundaries, which is given by this parameter zeta. So the degrees of freedom are the dilaton and the coordinate locations of the boundaries. So phi and zeta then encode the effect of the Casimir energy that we are interested in. So in particular, because of this non-zero Casimir energy, the dilaton configuration changes. And then also the coordinate locations of the boundaries change to some new location zeta and nu, so that this boundary condition of fixed dilaton is satisfying at the boundary. So then we can state our question of interest more concretely, which is that in the presence of this Casimir energy, what are the possible boundary trajectories or boundary embeddings for which the dilaton value at the locations of the boundaries is equal to the value that we're fixing it to. So that's the question we're interested in asking now. And then in all of these embeddings is the space-time taller or fatter compared to before. So before I move on to computing the Casimir energy, let me just say what exactly I mean when I say tall or fat. So the basic principle behind the space-time getting taller, which just means that the Penrose diagram gets taller. The basic principle behind that is that you have an increase in causal connectability between the two sides. So here is my starting setup where we have some two disconnected time-like boundaries, and you can see that we cannot send a signal from one boundary to the other. So one way in which the space-time gets taller is that you will be able to send a signal from one boundary to the other, as pictured here. However, another possibility is that the light cone of some particular point on the boundary expands. So this point on the boundary, at the moment of time symmetry, is able to probe more of the space-time compared to before. However, it's still not causally connected to the other boundary. So I'll be calling this situation weakly taller, where it's a matter of definition. So similarly, the space-time can get fatter, which means that no two points on the boundary are causally connected. So not even the points that are at E equals negative infinity and E equals positive infinity on either boundary. And similarly, the space-time can get weakly fatter, which just means that the points at negative infinity over here and positive infinity over here are still causally connected. However, the light cone of some point on the boundary contracts and gets shorter.
These two boundaries are fixed area, right?
Or fixed dilaton.
Yeah, so I'm confused how they reach the future infinity. Like they seem to, the point where that curved line intersects future infinity, like curved line says that the area is finite and the future infinity says it's infinite. Confused how that's consistent.
I guess these are cylinders that have some fixed proper size that are, from the higher dimensional setup, they're placed around the pole. And their sizes.
Another way of saying it is that the size of this thing is smaller than the visitor horizon, right?
Mm-hmm.
But you've drawn a line, a diagonal line, which is fixed visitor, I mean, which hasn't involved the visitor, empty visitor at any time. So your curved line, I think, should stay to the right of that.
Mm-hmm.
I was a little bit having trouble understanding what weekly taller means.
Weekly taller is the bottom right picture, right?
Right. So weakly taller, right. So for weakly taller, the two boundaries are still causally disconnected compared to the.
Weekly taller just looks to me like the original Penrose diagram of visitor space.
Right. So in some sense, it's similar because if you take the combined light cone of the whole boundary, it's still the same as compared to earlier. However, if I see what part of the space-time this particular point of the boundary can probe, that part expands compared to before.
But this is exactly a square, right? I mean, that's what the diagonal lines sort of clarify.
Right. So from the point of view of the Penrose diagram, it is exactly a square because the metric is not changing. But if we consider tallness as telling us something about causal connectability, then there is a change.
The Penrose diagram is the same as before, then the causal structure is exactly the same as it is.
If you're changing something about the stress energy,
points on the, if we consider what points on the, let's say we consider the past boundary and we consider what points on the past boundary this point on the timelike boundary can receive a signal from, then it can receive a signal from certain more of the past boundary than it could have in this picture. So that's some change.
The normal structure of the space is fully encoded by the normal diagram. So since this is a square, it is exactly by definition the same place.
Would you agree
Something
that
about the
there's-
metric structure may have changed, I'm not sure.
I think she's hoping to fix the intrinsic geometry down there, including the analytic transition and adding some quantum energy use which ends up being like that.
The definition of the
Is that the stable structure or different? So it's only the metric system or is it the other structure?
Well, there's where the boundary sits in the picture, and then there's what the underlying picture is.
Yeah, the boundaries change. It might be based on the definitions of causal structure. So, this one I'm trying to say is there's some difference between these two pictures. Maybe,
Maybe one way to think about it, can I think of just giving the exact same purpose diagram that you have in the middle, but just bringing the boundary?
yeah, that's exactly what's happening in the
So
bodies.
the lines of constant data boundary are a little bit, go deeper into the static functions. And so points on the constant data slices can receive signals from more points of the past boundary and send signals to more points of the future boundary, but the full categorical data is the same.
Might be that your confusion is based on the definition of causal structure.
I don't think I'm going to use the
Okay.
structure. Using diagrams.
But if you delete the gray lines, you will just get another diagrams, right?
Because one looks thinner than the other.
Yeah, you're deleting.
Timelike boundaries are closer to the center.
And that has meaning because there's metric information you're using
Yeah.
as well. So it's the rigid, the same, the diffeomorphic geometry, the path to where the boundary lies, means it's meaningful the location of the boundary, but it's really very metric structure, not just the causal structure is the same.
So it's the metric information about the size of the sphere that we need to add to make the decision.
So it's a meaningful comparison with how much of the sea relies on the top boundary.
That makes sense.
You're keeping that fixed, but what you're changing is the,
Yeah, hope it's clear now. Thanks. Okay. Okay, so just as a summary, the situation where it gets weakly taller is that these two boundaries are still causally disconnected. However, since the boundary locations have changed, the light modes of the part of the space-time at some point of the boundary in the probe has expanded. Okay, so next we can move on to the actually computing this Casimir energy in the space-time with timelike boundaries and seeing what its back reaction is on the space-time. So just as a reminder, we have some matter CFT on this curved background with timelike boundaries that has the de Sitter metric. And here we've written the de Sitter metric in a way that's conformal to flat space. And on this matter CFT, we impose conformal boundary conditions at the boundaries. And that means that these boundary conditions are invariant under conformal transformations. So one example of this is that the value of the CFT field on the boundary is fixed to 0, or the normal derivative of the CFT field is 0 on these boundaries. And then in this setup, the goal is to compute the expectation value of the stress tensor in the vacuum state, which is the Casimir energy, and where the boundary conditions on the matter are imposed at these locations, that in these coordinates are time dependent. So it's not immediately obvious how to do this, so let's instead move to a simpler setup where we do know how to compute the expectation value of the stress tensor, which is a boundary CFT living on a strip. So here the boundaries are located at these vertical positions of constant little pi, and the metric is given here by an expression that is conformal to flat space. So we can first find the expectation value of the stress tensor in flat space on this metric, and then perform a Weyl transformation to find the expectation value of the stress tensor in curved space. So for doing that, I've written the formula here below. Our goal is to find this expectation value of the stress tensor that is in there. So how do we find mu for a CFT living on a flat strip? We start on the upper half plane where we restrict the complex plane to the region where the real part of z is greater than 0. So that's this region. And then we do some conformal transformation that maps the positive real axis to one boundary of the strip and the negative real axis to another boundary of the strip. So then we can just, using the fact that the expectation value of the stress tensor on the upper half plane is 0, we can just find the stress tensor expectation value on the strip using the Schwarzschild derivative, which tells us how the stress tensor transforms under a conformal transformation. So now we can go back to our previous slide and use the fact that use the Y transformation formula to find the green stress tensor, which is the stress tensor on this curved geometry instead. I'm putting it all in, and for the Sitter space e to the 2 omega is secant squared sigma, we find the expectation value of the stress tensor on the Sitter strip. So why am I doing this? Why does finding the stress tensor expectation value for a CFT on a strip help us? The reason is that we can find a coordinate transformation that takes these sigma-dependent boundaries to some time-dependent locations. Now it's not just important that in these other coordinates the boundaries are located at some time-independent locations, it's also important that in these other coordinates the metric is conformal to flat space so that we can use all the technology we built so far for the flat space. So now we can start on this setup on the right-hand side where we have a matter CFT living on a curved strip where the metric is conformal to flat space. We can find the stress tensor expectation value using the conformal transformation from the upper half plane, followed by Weyl transformation, and then we can just do a coordinate transformation to this setup where we have these boundaries at the sigma-dependent location. And if we restrict to one patch of this space-time, we find that the stress tensor expectation value is given by this expression C over 24 pi times g mu nu plus some boundary term. So interestingly, this bulk term is independent of the locations of the boundaries for a conformal field theory, and the reason for that is that this coordinate transformation defines some conformal Killing vector in this space. Okay. So now that we've computed the Casimir energy, we can move on and find the back reaction of the space-time and see what happens to the locations of the boundaries and whether the space-time gets taller or flatter. So just a reminder, the dilaton will change in response to this non-zero stress tensor. So in particular, the dilaton changes from some initial configuration phi sub r sine rho to some new configuration where we have an in general unfixed constant phi sub r prime times sine rho plus c over tau. And then as a response to this change in the dilaton, the coordinate embedding of the boundaries, which is a meaningful variable here because the metric itself is not changing, the coordinate embedding of the boundaries change so that the value of the dilaton on them stays fixed to this value of phi sub r times tan zeta. So that's the meaning of this equation below, where zeta nu describes the new coordinate locations of the boundaries, and that's related to this parameter phi sub r prime and the parameter phi sub r, which is a measure of the horizon entropy, and zeta. So then for different phi sub r prime, a range of embeddings of the boundary zeta sub nu are possible. And for instance, one can imagine fixing phi sub r prime using some conditions for the dilaton at the past or future boundary of the space. So then what happens? Does the space-time get taller or flatter? The answer is that it depends on this parameter phi sub r prime. So here I've pictured phi sub r prime minus phi sub r. And for this parameter being greater than this value, negative c over tau times zeta, the space-time gets weakly flattered. It just means that this boundary point becomes causally connected to less of the space-time. So in blue we have the original locations of the boundaries, and in orange we have the new locations. And as we can see here, the light cone of this point contracts compared to before. However, there are also regimes where the space-time gets weakly taller instead, which means that the light cone of some point on either boundary expands instead. So you might ask, we haven't really fixed this parameter phi sub r prime here, is there some additional principle that we need to fix that parameter? The answer is that would be very nice, and if anyone has suggestions, I would like to hear. But in general, we have this whole space of solutions that we can get by imposing different kinds of initial conditions on the data. So if we want to probe this effect using some quantity in some putative holographic dual, we can also imagine computing two-sided correlation functions that probe the proper distance between these two boundaries. So because the effect of this matter is some change in proper distance between the boundaries, this will have an effect on two-sided correlation functions of this form that are given by e to the minus m times the proper distance between these boundaries. Okay. So just to summarize, today I talked about the Gao-Wald theorem and its effect on de Sitter with timelike boundaries. And in particular, this theorem predicts that it's possible to send a signal from one pole of de Sitter space to the other in some excited state of the matter, but not in the vacuum. And the question is, how does this change in the presence of observers or timelike boundaries? And can we make some qualitative predictions for the putative holographic dual? And the answer is that this Casimir energy, because of the observers or boundaries, back reacts to change the causal structure of the vacuum state. And in dS-JT, we can compute this stress tensor expectation value exactly and find how that changes the dilaton and the embedding of the boundary. And in particular, a whole landscape of boundary embeddings is possible as a result, and we find multiple kinds of solutions that are both weakly taller or weakly fatter, as opposed to just a fatter solution as might be naively expected from negative Casimir. So, to end with some future directions, it would be nice to study more general situations such as higher dimensions or where the matter content is not a CFT, to see if this weakly taller or weakly fatter effect is just some relic of having a very symmetric situation. And then it would also be interesting to consider quantum corrections to the Gao-Wald theorem in higher dimensions. For instance, what are the effects of the renormalization of G? So in particular, it's interesting to consider this because we want to understand what sorts of features the quantum theory of de Sitter space has. It would be interesting to have some boundary side understanding. What is the quantum mechanical origin of this effect? So in 2D, these authors worked out the generalization of the DT bar plus lambda 2D formation, and that provides some setup where we can study this. And finally, it would be interesting to study the effect of this Casimir energy on the stability of the bounded static patch, which in the canonical ensemble has a negative specific heat, but not in the microcanonical ensemble. In this particular ensemble, it would be interesting to study its effect on the stability. So thank you, and I hope you enjoyed the talk.
So have you thought at all about double trace like deformations in the setup? For example, one potential probe of the boundary getting, or the diagram getting weakly taller might be that you need a weaker deformation in order to actually construct a traversable wormhole, or something along these lines.
Yes, that's an interesting suggestion because usually we need some kind of double trace deformation makes the two sides causally connected. So if there's an analog, I haven't thought about that, but that's an interesting suggestion.
I think this might be related to earlier questions, but it seems that the fact you can compare the weakly taller and weakly fatter relies on the fact that the matrix is not backreactive in JT, so that you can meaningfully compare these zeta coordinates.
Yeah, exactly. Yeah.
So do you have any idea how these generalize to other cases, where the metric also changes?
To higher dimensions?
For example.
Yeah, so we can also generalize this to higher dimensions in sort of a similar way. Like in higher dimensions, instead the matter would back react on the metric, and the metric would change, and then you could see how null UD6 would behave in that new metric. Does that answer your question?
I guess maybe another comment is that you were asking how to fix phi r prime. That's a very naive idea. Maybe you can fix the de Sitter entropy to be invariant.
Yeah, that would be one way to fix that. But if there is one principle, then the only way to fix it doesn't be issues.
You were mentioning like a
Sorry, then phi.
Than high. If you
Oh,
let it
okay.
be wider than high.
Um,
Because that would violate the generalized second law. It would have consider a horizon that eventually hits infinitely large spheres at square minus.
So does this generalized second law take as an assumption the average null energy condition or
I
something?
think you can take it as an axiom. I mean, if that's wrong, then all of something less than gravity would be wrong.
Here is because here we violate the average null energy condition, so,
Yeah, so the generalized second law is supposed to be robust against this.
okay, interesting.
So,
Okay.
So yeah, if you go 2 slides back, you mentioned that the two sides become connected if you consider the side state of DC. By that you mean that you consider the shock wave from one side.
The shock wave could be one example, but any kind of matter content would also work.
Yeah, but suppose we take the shock wave example. Is the statement modified by including this quantum correction to the president? So now if I take your
Yeah, exactly. So it could be modified because that's another source of stress tensor you have to take into account apart from this shock wave stress tensor source.
But not polarity, right?
Sorry?
Not polarity, right? Because the shock wave is
I actually didn't understand.
oh, not polarity changes by wave, but
so it's just the amplitude of the shock wave.
or whatever the quantity may change, but the structure of the photo. Okay, with the shock wave, I mean, just evolve.
Yeah, I think in higher dimensions the causal structure might also change because the method would
Yeah.
change. But, yeah, I'm not sure if that answered your question.
Look at the dS-JT, the calculation that resulted in the weekly pattern. And then you said that the actual ds calculations for the theorem says that the ds spacetime should get taller.
So the
So can't we get dS-JT from the dimensional reduction of the ds? So have you thought about how does the ds getting pattern taller become the ds pattern in the context?
So you're asking how this would affect results from some dimensional reduction?
Because it seems to be opposite when you go to the JT.
So I guess here the idea is that this pattern effect is because of some negative energy instead of being in de Sitter JT in particular. So we might also find pattern solutions in higher dimensions, for instance. Then it would be interesting to see how that behaves under dimensional reduction. We just remove one dimension, so the Penrose diagram would be the same. This effect is not specific to de Sitter JT, but like it has to do more with violating the assumptions of the Gao-Wald theorem, which is the average null energy condition.
Okay, let's thank Gauri. So we're a little behind with this, as expected, I would say. So let's plan to reconvene at 5 till 11:55. There's coffee, I guess, in the back.
We're gonna keep it out here, but we encourage folks.
We would encourage you to go outside. There's like a nice patio with TV